Good morning, dear student. Now we are studying the nanoparticle synthesis. So I would like to first acknowledge to Mayur D. Chavan sir. So I have taken this presentation from uh, the part of the synthesis of nanoparticle from this uh, presentation. So I would like to thank him for the presentation. It is not I have not prepared it. So I would like to acknowledge him. And now we will see a quick recap of the yesterday's lecture. We have seen yesterday the method based on the evaporation. We have seen some theoretical part of it. Then uh, we have studied the structure of these evaporation methods, how they are using by using tungsten and other. Then crucible is there, and then what is meant by monolayer and multi-layer. So that we have studied in the last lecture. Then we have seen the advantages of the electron beam over the direct heating or using other methods. Like for the heating, we can use the laser and electron heating. So in this case, then they can use the resistive heating, electron beam heating, laser heating, and spruting. So out of this, the electron beam is the best one. It has several advantages over the other methods, so that we have discussed. Now today we will discuss about the physical vapor deposition. So physical vapor deposition. So before that, I would like to show you this figure of this the instrument in which the liquid nitrogen cooled central rod. So this is the central rod and which was cooled by liquid nitrogen. So liquid nitrogen temperature is minus 71. So so it will as uh, the temperature of this chamber is increases to reduce the temperature of the system. So we have used liquid nitrogen, uh, uh, cool rod, central rod, then scraper. So see, this scraper is for the removal of the nanoparticle from this rod, and then cold finger. That name itself suggested that its temperature is lower. So this is the funnel, and this is the crucible where the nanoparticle were moved. This is the gas inlet. So gas we can use it some inert gases, and these gases will react with these our gaseous nanoparticles, and it will form a uniform nanoparticles. So this is the vacuum pump. Vacuum pump, you know that all the air from this chamber can remove from this outlet. Then piston and wheel. So these are the component is available in the physical vapor depositor. So important is the source of evaporation, and then an inert gas or reactive gas for the collision with the material vapors. Then the cold finger on which the cluster or nanoparticles can condense, as we have seen cold finger. So here the nanoparticle on cold finger get deposited. So this rod itself is known as a cold finger. So then the scraper to scrap the nanoparticles, as we have seen this scraper, uh, this one to scrap the nanoparticles, and then piston and wheel, an arrangement in which nanoparticle powder can be compacted. So this nanoparticle uh, powder we can collect it in the piston and wheel. So usually metal or high vapor pressure metal oxide are evaporated from the filament uh, or both of the refractory metals like tungsten and the other molybdenum, in which the material to be evaporated are held. So uh, basically we have to evaporate the metal by using this tungsten molybdenum, and the metal in the form of the if it is solid, so it will get evaporated from the gas. So the density of the evaporated material close to the source is quite high and the particle size is small. So the vapor density is more. Density means the number of particles. So in the surrounding, the number of particles are more, but the size is very less. The material size in the vapor state, it is less than 5 nanometer. So such particles would prefer to acquire a stable lower surface energy state. So the law of physics is there. So according to thermodynamics also, so material wanted to get uh, more stable form. So lower energy state is more stable. So the vapor particle form wanted to get stabilized by using losing its energy. So such particles would prefer to acquire a stable lower energy state. So hence, due to small particles or cluster interaction, bigger particle get formed. Therefore, they should be removed away as fast as possible from the source. This is done by forcing an inert gas near the source, which remove the particles from the vicinity of the source. So this gas, so this inert gas like N2, so that they can use wanted to remove the nanoparticle form, because in the vapor state they get separate out and form the small particles, and they combine together. Due to the stabilization, they get combined together and with this inert gas, so they can be forcefully come together and then precipitate down. So in general, the rate of evaporation and the pressure of the gas inside the chamber determine the particle size and their distribution. So particle size means the nanoparticle size whatever we want, and we can change it by using the pressure of the gas, like they are saying. So if you wanted to rate of evaporation and the pressure of the gas inside the chamber determine the particle size and their distribution. So particle size, if there is only one size like 100 nanometer particle, if you want, we can uh, uh, utilize some gas pressure. At that time we will get only 100 100 size nanoparticles, but the size of the other also, but the size may be vary. So this can be controlled, particle distribution and the particle size, by the pressure. And then the distance of the source from the cold finger is also important. So these two important factors are there to determine the size, distribution, and their distribution. So pressure of the gas and the uh, cold finger distance, distance of source from the cold finger. Evaporated atom and cluster tends to collide with the gas molecule and make bigger particles which condense on cold finger. So as we have seen, so the vapors of the this material form, the gas material of the metal form, get condensed on the cold finger because temperature is less. Like similarly, if you boil the water on the gas, and if you keep some uh, cover on it, a plate or something, then the vapor get condensed on the plate. So similarly, the vapors of this material, which is our nanoparticle, get condensed on this cold finger, and then this cold finger, together with the gas molecules, get condensed here, and then with this scraper we can remove it, and this will mm, might be come to this crucible funnel. Vapor atom and cluster tend to collide with gas molecule and make the bigger particle, which condense on a cold finger. So while moving away from the source to the cold finger, the cluster is grown. So if the cluster have been formed on an inert gas molecule or atom, on reaching the cold finger, gas atom or molecule may leave the particles there and then escape the gas phase. So if reactive gases like O2, H2 and ammonia like oxygen, hydrogen and ammonia gases are used in the system, evaporated material can interact with the gases forming oxide, nitric or hydride particles. Alternatively, one can first make metal nanoparticles and later make appropriate post-treatment to achieve the desirable metal compound. So from this we can make the metal nanoparticle like silver, gold and other ferrous and then zinc nanoparticle. But if you want oxide of this metal, so it is very easy with this paper deposition method in which we can pass oxygen, hydrogen or ammonia. So we will get a respective oxide, nitride or hydride from the respected metal. So this is one of the very good method to get the nanoparticle as well as their oxide forms. Then alternatively, one can first make metal nanoparticles and later make appropriate post treatment to achieve the desirable metal compound. So this is the advantages of this method. The process of evaporation and condensation can be repeated several times until enough quantity of the material fall through a funnel in which a piston anvil arrangement can be provided. So this is what uh, we have discussed. The nanoparticle get dropped here from this, so it will get scratched and dropped here, and then we have to remove it. And this is the piston anvil used to remove our nanoparticle. So as much as of nanoparticle we can obtain from this method. So this is very good method, the very good method to obtain the nanoparticle of a size less than 100 nanometer, and the evaporated material size, as if we have seen, it is a more than 5 nanometer, but still the after condensation the size might be increases 10 nanometer to like 100 to 100 nanometers. We can control the size by the controlling the pressure, and then we can make a oxide of these metal nanoparticles. So this is are some of the advantages of this method. Uh, so today we have seen this. Tomorrow we will move toward the ionized cluster beam deposition method, and then we will solve some of these uh, problems related to the nanoparticle synthesis method. So I will give you MCQs, some of the MCQs on this chapter. So you have to solve it. So thank you all the students.